Hello students, welcome back. We went through section 1, including the optional part, the types of errors. Optional, yes, but it's optional for one type of method. For the method I'm going to take right now, this is not optional any longer, so let's review this. There are two types of errors. We'll have to select H0 or HA one way or the other, and also one of them must be right, one way or the other. So there are four possible choices out there. H0 is right, and then calling H0, in which case, no fault, no error. H0 is right, but I called HA, so I made an error. That is type 1 error. H0 is right, but I rejected it and called HA. Now, what about HA is right? If HA is right and then I called HA, then no error here. I did it right. If HA is correct, yet I rejected it and called H0, then that's an error. That's called type 2 error. So here, null is right, but I rejected. Alternative is right, but I rejected. Those are type 1 error and type 2 errors. Are there any other types of errors? No, there's not, because you see, there are all four choices out there, and the two are non-errors and two are errors, type 1 and type 2. Now, what are the maximal probabilities of those type 1 error and type 2 error? Maximal probability for type 1 error is called alpha, the level of significance, and that is actually the maximal conditional probability. Even though H0 is right, I rejected it and then accepted HA. So it's kind of like this. In criminal justice system, H0 is not guilty, right? Null is not guilty. So even though the defendant is not guilty, innocent, it was rejected and then HA went for guilty verdict. So we sentence a certain innocent person guilty. That's type 1 error. Pretty bad, isn't it? Now let's go to type 2 error. That 2 is a conditional probability in reality. Even though HA is right, that is guilty, that's rejected. Not enough evidence, so by default, let's go to H0, so presumed innocence. So even though the defendant is guilty, we let him walk free. That too is not very good either, but compare. Sentencing guilty verdicts to an innocent person versus letting a guilty person go free. Which is worse? This is far worse, and this is something we have to control before anything else. And then, if we can afford, we can do this, hopefully. That's the idea. We want to control alpha. We want to get as small an alpha as possible. So those should be 0.05, 0.01, things like that. And that value is called the level of significance. Now let's apply that to the hypothesis testing for population means when we can use the normal table. Here's a review of the checklist. In a simple random sampling, if you have large sample size, then you can use the normal approximation due to the central limit theorem, so you can use a z-distribution. For small sample size, and if the original population is normally distributed, then depending upon whether you know sigma or not, you can use normal distribution, where SE is sigma over square root of n, or you can use t-distribution. SE is S over square root of n. Now, if the original is not normally distributed, that means you have to go back to sampling design stage and then take larger sample and do it over. So in practice, that's important, but in classroom, this is useless because you will have a problem with an answer one way or the other. Now, here's a similar version based upon our textbooks out there, a bit too verbose. And all right, armed with all those, let's go to this example problem. Please stop the playback and go through its reading. The drying time of a type of paint under a specified test condition is known to be normally distributed with a mean value of 75 minutes and a standard deviation of 9 minutes, blah, blah, blah. Wait a minute, haven't we seen this before? It's right here. We went through this before, so let's set up appropriate hypothesis as we did before, and that's right here. Let's copy and paste that. I guess it's okay to do this because we went through this already. So null is about 75 minutes, and then alternative, no, less than that, because after all, the problem said you want to decrease the drying time, and also the sample mean is 72.3. Now, how about these? The standard deviation of 9 minutes, and then n is 25, so sample size, x bar, the sample mean is 72.3, and alpha is 0.02 as required. All good. But there's one problem here. This. Population standard deviation of 9.0. Does a problem specifically say this is a population standard deviation? Read problem carefully. It never says so. But how can we say that? Well, that's because the standard deviation of 9 minutes, this information came along with the null. So, normally distributed with a mean of 75 minutes and the standard deviation of 9 minutes. They're all together along with the null. What do you mean by null? Null is none, nothing. You didn't do anything. You didn't take the sample, so it did not come from sample. It is a population standard deviation, even though the problem did not specify it. I mean, if the problem specifically says population standard deviation like this, then that will make the problem too simple. In practice, you're not going to see a problem like this. They'll look like this. Whereas the information about the sample is right here. The mean drying time of 72.3 minutes with 25 observations. It did not specify this is sample mean, but still it's not too difficult because it came with 25 observations. But, you see, what if I change a problem like this? So the original distribution is normal with a mean of 75 minutes. Stop. And then blah, blah, blah. The mean drying time of 72.3 minutes and the standard deviation 9 minutes in 25 observations. This problem did not specify this is sample standard deviation, yet still you should see that you're talking about the sample distribution or sample standard deviation this time. Why? Because the standard deviation of 9 minutes, this information came with the sample. In 25 observations, you got 72.3 minutes and standard deviation of 9 minutes. It's a sample standard deviation. See the difference? Neither version of the problem, this is the original and this is the variation I just created, neither version specified population standard deviation or sample standard deviation. They just place the information in appropriate place so that you can see whether it's population standard deviation or sample standard deviation. Tricky, isn't it? For this one, you have to use t distribution. For that one, you have to use the z distribution. Here, we are using the z distribution. Okay, let's resume. And we talked about, let's see, we have two methods here, critical value method and probability value method. Now, fair warning, students who take critical value method usually score better. That was my experience. I've been teaching statistics in college level since 2001, so it's been over 20 years. And I've experienced of many semesters, and over the years I found that students usually do better this way. Me personally, I do it this way, second method, and all the textbook authors prefer the second method. And somehow maybe you prefer the second method too. And the reason second method is more preferred by professional mathematicians, that's related to what we just did. That's related to this theoretical foundation, type 1 error and type 2 error. Okay, let's begin. For probability value method, the setup we discussed, and here is the setup. So the center is the expected value of 75, and then we got sample mean of 72.3 minutes. And then, what is the probability that I end up with 72.3 or less, assuming the null is right? So getting something like this purely out of luck, assuming the null is right. What is that probability? And compare that probability with the maximum allowed probability of type 1 error, alpha. So if this probability P is greater than alpha, then it exceeds the maximum. So what's the conclusion? Okay, there's a hard part. It's not that clear. It exceeds the maximum, so you have to go with H0 because type 1 error is getting too big. Here, that's type 1 error, and it exceeds maximum. So type 1 error is probability, the conditional probability, giving guilty verdicts to innocent person, basically, rejecting the null hypothesis even though it is right. So calculate that P, and then compare with the alpha. P is greater than alpha, then type 1 error is too big. So you cannot reject the null hypothesis because type 1 error is too big. So you just go with null hypothesis. And p-value is less than alpha, then you do the other way around, like this. Calculate the probability by calculating this z-score and the minus center over SC and calculating the z-score. Simple computation, I'm going to leave the detail to you. And then work out the z-table. When you have z-value, then look up the z-table, and then you can find out the left-hand side shading, the probability. And that probability, which I'm going to leave to you because by now, working out the z-table should be comfortable for everybody. So you should be able to do this and get up to 4 decimal digits, all right? And then that's greater than alpha. So the probability of type 1 error is too big. So type 1 error is too big. So what do? It's bigger than the maximum allowed. That's the hard part. P is bigger than alpha. So we reject the alternative and accept the null. Not entirely correct, but a good way to work out this is to do it this way. This probability value is, roughly speaking, the probability that the null is right. It's not exactly equal to that, roughly speaking. Roughly speaking. So if this probability is big, then probability that null is right is big. You go with null. It doesn't always work this way, and this is not always correct, but most of the time it works out. If you're comfortable with this method, particularly if you like this type 1 error and type 2 error, you're comfortable with it, then you're going to like this. I do, and our textbook authors like too.